Hey folks, I hope you guys are having a good Wednesday. Yes, it is Wednesday. Okay, great. I hope you guys are having a good day. I hope that you're keeping up with material. I apologize, I did not post the problem set yesterday. It will be posted later today. I'm going to finish up that and post it after our class, around the time that I post our recording. That's the word that I was looking for. Um, Today we are going to be wrapping up glycolysis, and after that, then we'll move on to lipids and membranes. Um, and I think we're moving along pretty well with the content that I want to cover. Whenever I look ahead to the lipids and membranes, you know, if we can make it through lipids, I think we're going to be in good shape. If not, we're still in good shape because we still have Friday. But I'm just thinking ahead, like, well, the earlier that we cover stuff, probably the better for everyone. But I don't want to do that at the expense of like, oh well, nobody understood it, but I breezed through 712 slides. It was a really great class, and I am recording. I've got yep, it's recording. Got my screen shared. And here we go. Okay, so yesterday, just as a little bit of a refresher, we were going through our different phases of glycolysis. We talked about the two different phases. We basically made it through all of phase one, which our first phase is commonly known as the investment phase. The investment, and then the other phase is known as the payoff phase. Our wrap up point at the investment phase of glycolysis is none other than this molecule right here, glyceraldehyde 3 phosphate. Now, in the event that, and just so everyone knows, I do not have a second screen right now, and so that's one of the reasons that I you see kind of gray spaces covering your screen. I apologize for that. I will do my best to reduce that. Um, but I still want to, ask questions and get feedback from time to time. If anyone at any point feels the need to interrupt, by all means, unmute yourself, ask your question, or I've got the chat window up, um, and send me a message. So one of the things that I talked about yesterday was this step right here, our fructose 6 or fructose 1,6 bisphosphate, or FBP, being broken open and being converted to glyceraldehyde 3 phosphate and dihydroxyacetone phosphate. These are two 3-carbon sugars. One, two, three. One, two, three. Now, glyceraldehyde 3 phosphate, I think that it's helpful to, if I were to scribble these out, what would your tools be that you could go, oh, I know which one is which? Well, one tool that you have is you've got the functional groups. If you look over here on the left-hand side, we've got this carbon right here. And sorry, let me rephrase that. We've got this functional group, an aldehyde functional group. So between the two, which molecule do you think has an aldehyde functional group? Glyceraldehyde 3-phosphate or dihydroxyacetone phosphate? Well, it's right there in the name, glyceraldehyde 3-phosphate. Now, the other sugar, therefore, has our carbonyl at carbon number 2. And so one of the things that's important about this is that glyceraldehyde 3 phosphate and dihydroxyacetone phosphate, well, we're going to basically kind of, I want you to be able to recognize and identify these two molecules. One of the other things that I wanted you to know was that when we take fructose 1,6 bisphosphate and split it into two different sugars, we get one ketose and one aldose. We split those two, or we split that 1,6-carbon sugar into two 3-carbon sugars. Then our very last step in the investment phase of glycolysis was to take dihydroxyacetone phosphate and convert it into glyceraldehyde 3 phosphate. Now, that was a point I remember as an undergraduate and my first semester as a graduate student kind of struggling with. I remember being like, okay, cool. This reaction right here, let's just imagine that I did not have this figure over here on the left. This reaction right here, oh, it's reversible. Triose phosphate isomerase, or TIM. Yeah, that's reversible. Okay, cool. So I can interconvert glyceraldehyde 3 phosphate to dihydroxyacetone phosphate. Great, great. After that, it's all magic, right? Well, yeah, you can interconvert them, but is there one of these molecules that is more valuable for our next reaction? Yes, and it is glyceraldehyde 3 phosphate. So, in terms of this being a reversible reaction, it absolutely is. But in terms of, well, which direction do we want it to go? Well, we want dihydroxyacetone phosphate to be converted to glyceraldehyde 3 phosphate because we want to be able to continue through glycolysis. Now, that give or that whenever that clicked for me, that was really helpful because then I would say, oh, well, what are my next enzymes? Okay, so if I end the investment phase with glyceraldehyde 3 phosphate and I'm given, let's say it was a multiple choice test. If I'm given these three, if I'm given A, B, C, and D, A being glyceraldehyde 3 phosphate dehydrogenase, B phosphoglycerate kinase, C phosphoglycerate mutase, and D is enolase. If I know that I'm ending the investment phase with glyceraldehyde 3 phosphate, it makes it a little bit easier for me to say, oh, well, then A must be the next enzyme in the sequence because of the fact that the name of my molecule gap is in the name of the enzyme. So that was something that was very helpful for me. Now, when it comes to our classes of enzymes, we looked at all these different classes, these 6 different classes. I'm going to jump ahead because we kind of talked about those. The two enzymes that we do not encounter, or the two types of enzymes that we do not encounter in glycolysis, are our ligases and our, it's not a ligase, our ligases and our oxidoreductase. No, no. Okay. Well, a ligase and I think it might be, it's not a ligase, it's not an isomerase. Oh, our ligases and our hydrolases. Those two enzyme classes are not in glycolysis. Now, our first enzyme, just to kind of recap and bring it back up, we used hexokinase, which is a transferase. This is our first irreversible step. Can I get a number in the chat if you're good with yes, that is the first irreversible step, but it is not the first committed step. Now, that terminology, that not the first committed step, means that this glucose 6 phosphate can go here, can go here, can go different directions. It can go to glycogen. This metabolite can be used for glycogen synthesis. It can be used for the pentose phosphate pathway, and then it can also be used for glycolysis. So it can go in a number of different directions. It's dynamic, but this is an irreversible step. So we've got first irreversible step is catalyzed by a kinase. Okay. Our next step, our kinase, and a kinase is an example of a transferase. Our next step, we've got an isomerase. Oh, we're rearranging the furniture. That's that is a reversible step. We can go from glucose 6 phosphate an aldolase to fructose 6 phosphate, an aldose to a ketose. Okay, reversible, done. That is an isomerase. It's right there in the name, phosphoglucose isomerase. That is in the class of enzymes where isomerization or rearrangement of atoms within a single molecule takes place. Next up is a kinase. And lo and behold, we've got ATP, and we are transferring a phosphate from ATP onto our substrate, fructose 6 phosphate. Give me an I if this is an irreversible step, or give me an R in the chat if this is a reversible step. Wonderful. Now, one thing that I want to stress about reversible versus irreversible step is every enzyme catalyzed reaction, is it technically reversible? Yeah, technically. But the question is it energetically favorable to go and do the reverse reaction? When we classify a reaction as irreversible, that's effectively our way of saying that, hey, this could go backwards, but there's such a tremendous energy barrier that it's not going to go backwards. And as a result, does thinking from a physiological standpoint and an organismal standpoint, um, can you convert, like, can any of the cells in your body, give me a Y for yes or an N for no, can any of the cells in your body take fructose 1,6 bisphosphate and make fructose 6 phosphate? Give me a Y for yes, there are some cells that can do that, not with PFK, but it is possible they can do that. Or an N for no. Yeah, you're right. Absolutely, that can take place. In metabolism, you'll learn about this in the process known as gluconeogenesis. And that's important because if you think about, um, I would say maybe, and people might debate me on this topic, but I would say maybe the most famous Texan of all, and go ahead and add to the chat who you think is the most famous Texan of all, and I'll say my piece right now. The Liver King. The Liver King might eat nothing but organ meats, and I watched the Netflix thing. He seems organ meats and maybe just meat. Does he have any circulating glucose in his body? He absolutely does. I like the contribution of LBJ. I would just argue with that for forever. And I say that because I think that the, oh, okay, touche on Nolan Ryan. Alvin, Texas's own. Um, George Strait, no, no. I do not know where the Liver King is from, but I think it's like Kingsville area. It's definitely far south Texas. Wouldn't it be crazy if he was also from Alvin? Then it would be the Liver King and Nolan Ryan. What statue would you put up? I think I would do a hybrid, like split down the middle. One half is Nolan Ryan, the other half is Liver King. Oh, okay. And then Suzanne will also be a part of the statue. You can be standing there like this. Okay. Um, but if anyone wants to like go to the Alvin City Council and say, hey, my biochemistry professor said he didn't know where the Liver King is from, but he decided kind of arbitrarily that he's from Alvin. We should put up a statue of him. I will join you on Zoom for that meeting. Okay, so anyway, my point is to bring it back home. The Liver King, and yes, this is my point. The Liver King might eat no vegetables. Like his diet might be 100% meat. If you were to do a blood draw of the Liver King and were able to get some blood out, despite what I would imagine is a very large amount of cholesterol, if you were to get some blood out of there, and that I don't know, would he have glucose in his blood? He absolutely would, because your body has mechanisms to convert amino acids into sugars, and your body needs circulating glucose. So, gluconeogenesis is the process where you convert other things to glucose so that you can have glycogen stores. And the enzymes of gluconeogenesis, this is the great thing about learning glycolysis. As soon as you know glycolysis, you already know 70% of gluconeogenesis, because there's three enzymes that are irreversible in glycolysis, and those are the enzymes that are going to be unique in gluconeogenesis. Now, I I have no problem taking a little bit of an aside, spending a lot of time on this slide, because this is such a pivotal enzyme in glycolysis. It's our second irreversible step. I'm just going to label it IRR. It is, however, the first, I'm going to say, committed step. Because when you catalyze the conversion, or let me rephrase that, catalyze the phosphorylation of fructose 6-phosphate to make fructose 1,6-bisphosphate, the atoms that make up that molecule, their fate is sealed. They are going to end up in pyruvate. Now, let me go ahead and add a little bit of a qualifier. Their fate is sealed in the sense that provided that your body is in the exact same conditions and doesn't change, yeah, that's what you're going to do. Like if something were to change and I don't know, you got like a spike of adrenaline or something like that, then the situation might change, or you might, I don't know. If something catastrophic changed to the state that you're in, well then sure, things can be rerouted. But under normal conditions, when you convert fructose 6-phosphate to fructose 1,6-bisphosphate, that's going to pyruvate. Because that phosphofructokinase 1, or PFK1, that is the first committed step of glycolysis. You are going to pyruvate. Now, second irreversible step, first committed step, you need ATP because that's where your phosphate's coming from. One thing that you probably noticed was the presence of Mg2+. Now, Mg2+ is required for hexokinase and PFK1. Is that something I need you to lose sleep over? No, it's not. If you think about an ATP molecule, and I'm just going to go ahead and say, here's my base, here's my sugar, and then here's my nucleotide, or the phosphate that makes up my nucleotide. Okay, so we've got O, O, O. And whenever I'm drawing a nucleotide or a nucleotide triphosphate, I always think to myself, I'm kind of singing, oh, 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 it's magic for sure. But I'm doing it in a very boring way. Magnesium, Mg2+. It's an electrophile. What is it going to do? Well, it's going to hang out right here. And whenever it hangs out right here, it's going to help coordinate and properly position what are known as alpha and beta phosphates. So it basically holds their position so that this gamma phosphate over here can be transferred more easily. So you might be asking the question, well, is magnesium essential? It is. Is it like, could you substitute it for a different divalent cation? Yeah. Is the enzyme going to work as efficiently? No, it's not. But that's one of the things that this magnesium is doing. It's helping coordinate things. Now, I've said all that, and I think that kind of makes it an easy way to remember, oh yeah, magnesium, necessary. I'm not going to have any questions about which divalent cation is necessary for this, because that's kind of like a little bit of a trivial sort of question. Okay, so PFK1 is our third step. It's our second irreversible step. It's our first committed step. We've reached the top, the crest of the roller coaster. Now we're going to begin going down. In order to get there, we've got to have aldolase that takes our 6-carbon molecule to split it into an aldose and a ketose. Whenever we split our molecule into an aldose and a ketose, well, we're in a pretty good position. Now what we can do, however, is, and that was a lyase that did that, now we're going to employ an isomerase to rearrange that ketose into an aldose. What we want to move forward with is this aldose. We want glyceraldehyde 3-phosphate because the enzyme that we're going to use is an oxidoreductase. The enzyme that does that is highlighted right here. I've got 2 slides for this because this is kind of a rapid step. We have GA3P dehydrogenase, glyceraldehyde 3-phosphate dehydrogenase. Now, one of the things that's unique about this step is let's look at our starting molecule, glyceraldehyde 3-phosphate, and then let's look at our concluding molecule of that step. The biggest difference between GA3P and 1,3-bisphosphoglycolate is we've got a phosphate on here. Wait a minute. In all of our other reactions, when we are adding phosphate to something, they were kinases and they were transferase reactions. Well, that's because our phosphate donor was ATP. In this case, GAP or GA3P dehydrogenase, people call this GAPDH, which that's very valuable anytime you're talking about metabolism. It saves a little bit of time. What GAPDH is going to do is it's going to take this right here. Could anyone write in like the shortest shorthand, how would you label this, or how would you add this as a reactant in a chemical reaction? Add it to the chat. PI, inorganic phosphate. That means it's a free phosphate that's just floating around. It's there. Is this dependent on ATP? Nope. We do not need ATP for this. The phosphate donor here is simply inorganic phosphate. GA3P dehydrogenase, that word right there, dehydrogenase, that is a great indicator that you are talking about an oxidoreductase. You are talking about a oxidation reduction reaction. Now, what we're going to do in this process is we're going to take this NAD plus and we're going to make NADH. Now, thinking about NAD plus versus NADH, I think that most people, one of the things that they recognize about those two things, NAD plus versus NADH, is you can start low and say, well, one of them has a positive charge, the other doesn't. And you'd be right. One of them has an H and the other doesn't. If you think about the charges, one of them's positive, one of them's neutral. Okay. Now let's think about, I like to think about chromium, Cr. What's the difference between Cr and let's go with Cr2 plus? Well, one of them is neutral and one of them is positively charged. Now, between the two of these, could you say that one of them is the reduced form and one of them is the oxidized? Would everyone agree with me, and add a Y or an N, would everyone agree with me that, yeah, we use different terms of atom and ion, but effectively, these two things, Cr and Cr2 plus, are to a degree the same thing, or they originate, they have a common ancestor, I guess you could say. Okay, great. Now, that's important because we can apply that same logic or rationale to this right here, to our NAD and NADH. Now, what I want you to feel comfortable doing, and use this process, I do it myself. I would say, okay, well, Cr and Cr2 plus, I'm going to identify one of them as the oxidized form and one of them as the reduced form. Okay, so I got to go back to oxidation is loss of electrons. Oil. Okay, so oxidation is loss. So which one of these, Cr or Cr2 plus, has lost electrons? Well, I feel like this right here has lost electrons. And if this is the form that has lost electrons, then give me a Y or an N if you agree that the other one is the form that is reduced and therefore has gained electron in comparison. Spot on, perfect. Now, using that rationale, what I always do personally is I say, okay, if I see a positive charge on there, I'm thinking oxidized. So this is my oxidized form, this is my reduced form. The one that has no charge, that is neutral, is my reduced form. The one that has a positive charge is my oxidized form. Okay, can you give me a Y or an N? A Y if, okay, cool, I can follow that. Or an N if, wait, you lost me at oil. Okay, great. Now, that's important for understanding the context of, okay, well, we have our oxidized form of NAD plus making the reduced form of NADH. Our reduced form or our reduced form of nicotinamide adenine dinucleotide, the NADH, that has electrons. That's very powerful. That is a high energy compound. We like this, so we're going to save for later. And if at any point you're thinking to yourself, oxidation reduction reactions, that's not super exciting. Think about if you got, add to the chat and tell me what would happen if I had pure potassium or sodium and I dropped it into water. What's going to happen? It's going to explode. There's going to be a fire. It's going to oxidize very rapidly and release a huge amount of energy. That's what we are relying on here. So when we get to the electron transport chain, I mean, heck, you hear those words, electron transport chain, and you might think, wow, that sounds like maybe the most boring chain of all time. That's where I would say, not so fast. These electrons are being transferred from one thing to the next. Along with that electron transport or movement, we've got energy that's being transferred. Okay, so this oxidation reduction reaction has a couple of hallmarks. Anytime you see dehydrogenase, and there are a couple of other key words, or you see NAD plus and NADH, those are great indicators that you're talking about a redox reaction or an oxidoreductase. We've added a phosphate group to make 1,3-bisphosphoglycerate. And as soon as we have that 1,3-bisphosphoglycolate, what we can do with that is we can transfer this phosphate that we just added onto ADP. Now, a fair question is, well, why can't the inorganic phosphate just jump onto an ADP molecule and make ATP? That's an energetically unfavorable reaction. That's why. So PI plus ADP yields ATP, unfavorable. But when we get this phosphate and couple it with this oxidation reduction reaction, we get that phosphate added to glyceraldehyde 3-phosphate, and we make this high energy compound, well, then we can easily convert it to ATP. More easily make ATP. Now, my follow-up question is, to all of this, if we do this, if we reach 3-phosphoglycolate, how many ATP have we made? Add it to the chat, the number of ATP that we've made. And before you answer, think, well, how many glyceraldehyde 3-phosphates do we have? We've got 2. That's exactly right. This is the beginning of our return phase. So we're right here and right here. We started with 6 carbons. We end up with 2 glyceraldehyde 3-phosphate molecules. These 2 reactions are happening parallel with one another. So anytime you see this, this is actually happening twice because we plugged 2 of these in. So how many inorganic phosphates did we need? We needed 2. So when we have 2 inorganic phosphates, 2 glyceraldehyde 3-phosphates, we need 2 NAD plus to make 2 NADH and 2 1,3-bisphosphoglycolate. Once we have our 2 1,3-bisphosphoglycolates, well, phosphoglycerate kinase is going to transfer this phosphate onto ADP to make 2 ATP and 2 3-phosphoglycolates. Now, Answer in the chat if you understand the numbers and where they came from. Just give me a Y or an N. If you follow it, say Y. If you are confused about those numbers, please say N, and we can go back through that. Okay. Now, at this point in time, if you think about it in terms of glycolysis is like a business or something like that, we've generated 2 ATP. How many ATP did we invest? 2. We spent 2 ATP to phosphorylate glucose and to phosphorylate fructose 6-phosphate. Now we've got 2 ATP back. We are done in terms of getting the return on our money. Arguably, we are actually a little bit ahead because not only did we get 2 ATP so we can pay the bank back, but we also got 2 NADH. And those are high energy compounds that we're going to save for later. So one of the questions I like to ask is, at what step have you paid back your ATP debt? Oh man, I like that. I like that wording. Well, at phosphoglycerate kinase. Once you've made 3-phosphoglycolate, you're even. So that means if any more ATP can be generated from here on, well, that's fantastic. If we generate more ATP from that compound, well, then we're going to be kind of profiting. Now, looking at this right here, what type of enzymes did we just look at? We looked at an oxidoreductase, where we had oxidation reduction reactions taking place, and we looked at a transferase. Anytime you see that term, like whenever you see an enzyme that includes NAD plus, NADH, think about, okay, well, that's an oxidoreductase. Or if you see the term dehydrogenase, that's an oxidoreductase. Now, our next enzyme here, phosphoglycerate mutase. We're taking 3-phosphoglycerate, or 3-PG, and simply rearranging the phosphates. This is one of the reasons, This is one of the reasons right here why the payback phase is kind of boring. Because, hey, we've made our money back, and we made NADH, so at 3-PG, we're pretty good. Because all that we're going to do is rearrange the phosphates. We're going to move it from carbon number 3 to carbon number 2. Fun. Great. Then, once we've got that, we're going to use the enzyme enolase, where we're going to remove a water from this molecule. And whenever we remove a water, we're going to have a double bond between carbons number 2 and 3. Awesome. Great. This is exciting. We're going places. We're moving along. We developed this phosphoenol pyruvate, which is phosphorylated. This enzyme, this catalytic step is reversible. The previous one is reversible. The previous 2 are also reversible. Once we get to phosphoenol pyruvate, what was our end, or what molecule was our end point in all of this? Pyruvate. We've got phosphoenol pyruvate. That's almost like saying we've got a phosphorylated pyruvate. That's effectively what we've got. As soon as we remove the phosphate from phosphoenol pyruvate, we're left with pyruvate. Our last enzyme that acts in this is pyruvate kinase. This is our third irreversible step. And we make pyruvate. We also make ATP. How many ATP did we make at this step right here? How many times is this taking place? Well, we have 2 phosphoenol pyruvates. We're going to make 2 ATP. So this brings up, good job, y'all, an important point. Gross ATP produced in all of this, in this whole pathway. Add the number to the chat. What's our gross ATP that's produced? Perfect. 4. What is our net ATP produced? Perfect. It's 2. Wonderful. We get this molecule pyruvate, which can go in a couple of different directions. In yeast and in some plants, ethanolic fermentation. Then we've got lactic acid fermentation. And then last but not least, TCA cycle. Okay. Now, on a scale of 1 to 10, no, let's make it simpler. 1 to 3. 1 being, oh, I've conquered this. I know all of this. And 3 being, what's a glucose? Share your number with me. If you want, you can share it privately. Okay. I got to be honest with you, with the answer options and the range that I provided you, I kind of expected lots of 2s. Maybe I should have gone with a range of 1 to 10 because, well, my 3 was quite an extreme and my 1 was kind of an extreme. Now, what I want you to know about this, what the high points of this are, and there's a couple of, let me just make sure. There we go. I have some kind of tells. Like I'm not a poker player, but I have some kind of tells whenever it comes to when I cover something. Lots of questions that I have revolve around the irreversible steps. So hexokinase or glucokinase, which I'm going to get into glucokinase in just a little bit. Then phosphofructokinase 1 or PFK1, and last but not least is pyruvate kinase. Now, whenever I want you to think about those, 2 of those use or consume ATP. Pyruvate kinase, by comparison, makes ATP. Now, what that has to do with, that nomenclature has to do with the high energy compound that's being produced. Is ATP higher energy than what's being input or what's being generated? So what I would do is I would say, okay, what are all of my steps? What are the names of all my enzymes that make ATP? Okay, hexokinase, phosphofructokinase, and that use ATP is hexokinase and PFK1. Those use ATP. Then what I would say is, all right, what are the inputs and what are the outputs of those? What does my EC numbering relate to those? The chances that I ask challenging questions about phosphoglycerate mutase or enolase are pretty slim. So if you think about that in terms of, well, what questions are you going to ask about? I kind of alluded to this yesterday in the sense that my first priority is the investment phase, understanding how to get to glyceraldehyde 3-phosphate. My second priority was pyruvate kinase. And my third priority was this thing in the middle. In terms of that thing that's in the middle, well, the ones that are kind of interesting to me are steps 6 and 7, where we generate our 3-phosphoglycerate. And that's interesting to me because at that point we've paid off our debts. We're back to 0 because now we've generated the ATP to offset the ATP that we spent. That's kind of where my head is whenever it comes to these different pathways and comes to these different steps and, oh, what information should I prioritize over anything else? Now, I've got my 3 irreversible steps right here. Hexokinase, phosphofructokinase, and pyruvate kinase. These are the 3 irreversible steps. PFK1 or phosphofructokinase is an irreversible step. Irreversible step that is my first committed step. People mix up first committed step and irreversible step. They're not interchangeable. One thing, or phosphofructokinase is both an irreversible step and it is the first committed step. Can a kinase both add and remove phosphates? Yes, it can. That's a great question, Mila. That nomenclature, typically what you will see is the term phosphatase as a compound that removes a phosphate, but it has to do with what's being produced. A phosphatase, what it's going to do, so as an example, and we're not going into gluconeogenesis in this class, but the enzyme that removes this phosphate right here is known as FB phosphatase. So a phosphatase typically reverses the action of a kinase. And the reason for that is because a phosphatase is not going to make ATP, but instead what it's going to do is it's going to release inorganic phosphate and the other product. So to answer your question, Mila, yes, it can both remove and add phosphates. More common than not, you're going to see it adding. Okay. Now, does anyone have any questions about this figure that's on the left-hand side? Any of the steps in glycolysis, maybe even like, what sort of questions are you going to ask about this? What should we anticipate? And if email me and I'll get back to you as soon as I can regarding questions. Okay. Now, the next thing that I wanted to talk about was hexokinase versus glucokinase. I mentioned glucokinase, but I haven't really talked about it. What makes hexokinase and glucokinase different from one another is that the name, hexokinase, that hexo is by design. Hexokinase is a little bit less selective. This is an enzyme that is, I always like this word, it's ubiquitous. It's in basically every single cell type that you have. Because what it can do is it can phosphorylate a number of different hexoses. So it gives you kind of different fuel options, and it gives you the ability to, well, if it encounters mannose, it can phosphorylate mannose. It can phosphorylate fructose. Now, this right here is a Dr. Pepper. This is a zero sugar Dr. Pepper. Could anyone add to the chat what is a common sweetener for sodas? And you can use the acronym if you want, if you remember it. Aspartame, sorry, I non-diet sodas. That would be aspartame is a great artificial sweetener, a zero-calorie sweetener. But if you get like a Dr. Pepper, chances are it's going to have something called high fructose corn syrup, which some people label it as HFCS. High fructose corn syrup has a bunch of this right here, fructose. It's got a bunch of fructose. So if you're drinking a Dr. Pepper and it's like a regular Dr. Pepper, that's going to be your sweetener. Now, fructose, the F in HFCS, that can be phosphorylated by hexokinase. And whenever it is phosphorylated by hexokinase, well, you get fructose 6-phosphate, also known as F6P. Well, F6P versus G6P. These two compounds, fructose 6-phosphate, glucose 6-phosphate, they are metabolized in a different way. Fructose 6-phosphate, and this is something that people like to bring up as like, oh, high fructose corn syrup is bad. And yeah, it is. It is. Done. There we go. I'm stating my opinion on something. High fructose corn syrup is not good. And the reason that it's not good is because only basically 3 carbons from this fructose 6-phosphate go through glycolysis. The remaining 3 carbons, well, of course, this depends on if you're in like a fasted state or if you're in a fed state, but these 3 carbons can make their way into fatty acid synthesis. And in addition to that, glucose 6 phosphate or glucose metabolism is interconnected with things like insulin and monitoring blood sugar. Fructose 6 phosphate, not quite so much. So, at any rate, hexokinase can phosphorylate both glucose and fructose. It can phosphorylate any number of 6 carbon molecules or 6 carbon sugars. Now, it has a fairly low capacity, and whenever this happens, that's going to happen in like every single cell in your body. Now, by comparison, in a liver cell, you do not have hexokinase. Liver, a healthy liver is a good indicator of general health in the sense that, well, you need your liver to be healthy. You need it for metabolism of fats, you need it for metabolism of cholesterol, which is a lipid, and you need it to help your body know how much blood sugar or how much sugar is in your bloodstream. Glucokinase is the name of the enzyme that does the same thing. It, however, will only phosphorylate glucose. So when fructose rolls through your liver, glucokinase says, don't care, I don't phosphorylate that. Glucokinase has a high capacity. It has a Km of 10 millimolar compared to the Km of hexokinase of 0.1 millimolar. Wait a minute. Okay, so hexokinase, HK, if you give that 5 millimolar glucose, if you give hexokinase, that enzyme, if you give it a concentration of 5 millimolar glucose, I'm going to give you a multiple choice question. A, B, C. Tell me about HK activity. Oh. A says, well, your enzyme activity would be at 0%. B is at 50%. And I'm going to say Vmax here. 50% of Vmax, and C, I'll say, well, I'm going to say 60+% of your Vmax. So if you give hexokinase a glucose concentration of 5 millimolar, where is Vmax going to be? Is it going to be operating at with a Km? Yep. Okay. I'm not telling you guys what to do, but I think that you guys should all look into starting a band because you're rock stars. So well done. Now, with that said, let's switch it. Good job. Now we're going to give GK, or glucokinase, 5 millimolar glucose. Tell me the GK activity. And I'm going to go with below 50% activity. I'm trying to make sure that this is all, yeah. Am I at, yep. You're absolutely right. It's below 50% activity. And you might think, well, okay, I'm trying to wrap my mind around this. Give yourself the Michaelis-Menten curve. Okay, there's our curve. I'm going to adjust it a little bit. There we go. That's a little better. Vmax. And then Vmax divided by 2. Okay, so my Km is going to be 10. This is for glucokinase, GK. And my substrate is glucose. If I'm like right, I'm at 5 millimolar. I'm giving my enzyme 5 millimolar. That means I'm right about here. I'm at below 50% of my maximum velocity. Well, that's kind of strange. That's like, or one of the ways that I personally think about that is, what do you want your liver to be doing? Do you want your liver to be like sensitive to any subtle change? Or do you want it to just be ready to be like, okay, sugar is high. Now I need to store some, and then I need to make sure that I'm activating hormones so that I can ensure that everything else is operating. Claire, you're right. You don't want your liver to be like, oh my gosh, there's more sugar. I better do something. You want your liver to be there like, hey, I've got all of this stuff. I've got all of these different cells that are processing sugars. They are breaking down glucose. Whenever they need energy, they're going to say, hey, bloodstream, give me some of that sugar. Chomp, 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 chomp. That's my sound effect for metabolizing sugar. You want all of those cells to be ready to go. Now, you want your liver to be there in the event that the blood sugar level stays too high. Your blood sugar level in your main portal vein is about 5 millimolar. So glucokinase typically is not going to be super active, and that's fine. You don't want it to be super active. You instead want everything else to kind of pick up the slack and metabolize the glucose as it comes around. Whenever you go on a candy bar eating competition, whenever you're ingesting 6 pounds of Snickers bars, that's when you want your liver to be like, oh, we got a lot of sugar coming in. I think now is whenever I can help out to metabolize this, but also I want other systems in the liver to be ready to store that glucose as glycogen or store it as fat to, use this in some form or fashion. So when you think about like, oh, should hexokinase and glucokinase, should they have the same functionality? No, they shouldn't. They should be able to do the same thing, but one of them is kind of like almost like an emergency escape valve of sorts. So that's our difference between hexokinase and glucokinase. Hexokinase is everywhere. Glucokinase is reserved for your liver. Hexokinase consumes glucose all the time. It's ready to. It's ready to help out with every type of sugar metabolism, every 6 carbon sugars metabolism. Glucokinase is like, I don't really want to do that. I could. You know, I'm singing the praises of glucokinase, but there's a little part of me that's like, I know what glucokinase is. Glucokinase is my manager whenever I was in high school and worked at a buffet restaurant, where they would just sort of sit back and be like, you guys clean everything? Good, good. Joel, did you wash the dishes? Good, good. But when there's a rush, that's whenever I'm ready to help. No, oh. The softball team? No, that's not really a rush. That's not when we have 3 softball teams, then talk to me. And then it's like, hey, Scott, we got 4 softball teams. Oh, can't you see? I'm over here talking to the manager of Gold's Gym so I can get a free discount or a discounted membership when you guys make him omelets on the weekends. Can't you see I'm busy? So that's kind of glucokinase. But the difference is glucokinase maybe respects hexokinase and is like, I'm going to make sure that you have a livable wage. At any rate, here we go. Hexokinase, glucokinase. I hope that my analogy made some sense there and was not just, oh gosh, he's trying his stand-up bits, because I'm not. Okay. ATP yield. From 1 glucose, you're going to get 2 net ATP, 2 NADH. Scale that up. If you get 5 glucose, the math changes a little bit. 10. One of the questions that I always like to think about, and this would be like, I think that this is a good thing to kind of prime yourself for metabolism, is to think about, well, if I consume a bunch of glucose Well, then I'm going to invest ATP there. What if instead of consuming a bunch of glucose, I consumed a bunch of glucose, let me rephrase that, G6P? If all of the sugar that I took into my body was G6P as opposed to glucose, what would that mean? Well, one thing that would mean is I would skip over this step. So I don't have to invest one ATP there. So that means my net ATP. So if I were to consume one G6P, my net ATP would be 3 net. What about my NADH? Well, that's going to remain the same. But that's one of the things that I always found to be very helpful when it came to learning these different pathways and how they vary a little bit. To like plug yourself in. Well, what if I ingested a bunch of 3PG? What's going to happen? Well, for every 3PG molecule that I input, I'm going to get, well, 1 ATP and 0 NADH. That's not like, oh, is that an option? Can I go and get, a Snickers bar that's sweetened with glucose 6-phosphate? No. I just found that always to be helpful in terms of like looking at these metabolic pathways as almost like a roadmap of sorts. Okay, now if anyone has any questions, feel free to add them. But in the meantime, I'm going to be switching over to lipids. And so if you want to unmute yourself and ask questions, go for it. Otherwise, I'm going to lipids. And what we're going to do for lipids is we're going to get some definitions, and then we're going to look at some fatty acids, and then we're going to call it a day because we've covered a lot of stuff. And, yeah. Okay, so I'll drink a soda for a minute while I leave the floor open for questions. Okay. So lipids are biological substances or substances of biological origin that are soluble in organic solvents, unique and different from, well, amino acids, which are soluble in aqueous substances, in aqueous solutions. Now, lipids have 3 predominant functions. Lipids are parts of a lipid bilayer. They're essential components of membranes. Lipids containing hydrocarbon side chains are energy stores. And then last but not least, signaling. They're great for communication. Intercellular signaling events involve lipid molecules. Now, in terms of classes of lipids, there are fatty acids, triacylglycerols, glycerophospholipids, sphingolipids, and steroids. Now, if you think about these, if you hear these and you think, okay, well, what terms are interchangeable and what terms maybe are like familiar? If you were to go and get your annual physical, which is always a good thing to do, they're going to do a lipid panel. And on that lipid panel, you're going to get information about steroids, cholesterol being a steroid. You're going to get information about your free fatty acids and your triacylglycerols. Those are the 3 big things because those will give you a little bit of a sense, or those are biomarkers for, are you at risk of cardiovascular disease? Now, in terms of to switch it a little bit and talk about something that, I mentioned Liver King, so we've reached a new intellectual height in this class. If you hear about someone who eats a high-fat, low-carbohydrate diet, chances are they are consuming lots of these first 2, primarily fatty acids. Now, one rationale for that and one reason for that is, well, those have huge amounts of energy because a triacylglycerol is effectively glycerol plus 3 fatty acids. Now, Whenever I think about steroids, my first thought is like sports and the World Anti-Doping Agency and you know, cheating in sports. And then of course I think about, you know, arguing with someone who's like, well, I'm going to be the devil's advocate. And that's whenever I'm like, that's so funny you say that because I have zero interest in talking to the devil's advocate. You are advocating for the devil. So thank you, no. At any rate, um, whenever I think about steroids, I think about cholesterol. Okay, you know, I had a bag of a fun-sized bag of Cool Ranch Doritos, and this happens to have zero cholesterol. It's got 8 grams of total fat, but zero cholesterol. Cholesterol. What has a lot of cholesterol? Bacon and other animal meats. Um, in which case, the person who says, well, and egg yolks, the person who says, well, I eat a high fat, low carb diet, um, and I need that energy, you possibly do. It depends on what you're doing over the course of the day. If you're eating 3 cheeseburgers and you're running 7 miles a day and cycling 20 miles, yeah, you probably do. I don't know. But and then cholesterol is something that's kind of packaged along with that. Um, so glycerophospholipids and sphingolipids maybe aren't a part of a regular conversation like fatty acids and cholesterol can be. Um, Whenever I had my last physical done, I don't think that as, and I always try to make a point to look at it like, oh, what can I remember for my class? But you know, they don't mention anything about a sphingolipid or sphingolipids or glycerophospholipids really because those are compounds and molecules that are involved in signaling, and they have less of like a dietary benefit. But we're going to get into and talk about all 5 of these things. Now, with that said, where we're going to start out is we're going to start out with fatty acids. We'll kind of follow this pathway through these 5 different classes. Fatty acids, I think that I saw a fatty acid, or we drew fatty acids for the first time whenever I was in organic, because they have a long aliphatic chain, a tail, and a carboxylic acid, hence fatty acid. Now, these are examples of fatty acids. These that you see on the right hand side, I got to close my, or I got to move this over here. These are all 18 carbon long fatty acids. Now, one thing that I want you to recognize about these that isn't really a high priority, but is something worth thinking about, is this carboxylic acid. In a physiological pH or at a neutral pH, it's not going to be OH. It's going to be that. It's going to be deprotonated. It's going to be COO minus. Now, these 4 different fatty acids, well, it's possible that you've seen these names before. And the reason I say that is because, and we're going to come back to this slide, is because if you look at this table right here, looking specifically at the top, and then looking specifically at this column right here. Now, from my memory of Organic Chemistry 1, the very first experiment that we did was in Organic 1 was lots of like physical properties. The first experiment that we did was we had sodium borosilicate or glass capillary tubes, and then we had these powders. And we would get a little bit of the powder and put it into the bottom of that glass tube, and then you'd look through something. It was an instrument, and you would heat it up. There was a heat block, and you had those pieces of glass. Does anyone remember what that instrument is called? Add it to the chat. My description is absolutely perfect. So anyone who's doing this, what on earth is he talking about? A Meltemp. So that was, yeah, sorry about that. And I still need to add your bonus points. I apologize. So that was an instrument where you had these little glass crystals and you'd put it in there and you heat it up and you'd watch through this little this magnifying glass and you'd be like, at what point does it transition from a solid to a liquid? And you would record that. And I remember that experiment just being like, this might be more boring than watching water boil. It might. It very well could be. But in the process, we were learning a physical property. So in retrospect, it's like, haha, no, sir, Joel, you just didn't understand it. And that's the internal monologue that I have from time to time. But I bring that up because usually whenever you do that sort of analysis, you're using fatty acids because their melting temperatures can be considerably high. Now, these are examples of four fatty acids. They all have common names: stearic acid, oleic acid, linoleic acid, and alpha linolenic acid. I do not want you to commit to memory those common names. I will not ask you common names of fatty acids. Now, what I want you to notice about these is that the carboxylic acid, that carbonyl carbon, is your highest priority. So that gets carbon number 1. Now, the predominant length of fatty acid residues in plants and animals is between 16 and 18 carbons. Can they be longer? Yes. Can they be shorter? Yes. But more times than not, they're that range. They're either 16 or they're 18. Now, terminology that we use for fatty acids, we define them as saturated versus unsaturated fatty acids. This is something that, again, if you've had your annual physical, or if you've had an annual physical lately, this is probably language that came up. Or if you have a friend or you are a dietitian, what do most people, or what are most people suggested to consume more of? Saturated or unsaturated fatty acids? Unsaturated. Now, if we look at these unsaturated fatty acids versus saturated fatty acids, the way that I remember it is I think, okay, this molecule right here where I'm drawing an X, that has nothing but hydrogens and carbons on its chain. So I always think that is saturated with hydrogens. By comparison to A, B, and C, these all have at least one double bond. Now, the presence of these double bonds indicates that it is either an unsaturated or a polyunsaturated fatty acid. Linoleic and alpha linolenic acid are commonly known as PUFAs, polyunsaturated fatty acids. The FA for fatty acid, PU for polyunsaturated. So this is like, lipids are kind of part of a conversation that is where you see the overlap between the field of biochemistry and nutrition. These two fields kind of overlap a little bit because lots of the people who, like, right now biochemistry is kind of its own field. Back in the 1950s or so, if you called yourself a biochemist, well, really, you were a chemist that worked on a biological molecule. If you were a dietitian or in the field of nutrition, well, then you studied it from like a systems biology. How does a person respond to this? So we do see a little bit of overlap whenever we have this terminology. Now, for designating a fatty acid, the notation that we use is C18:0 or C18:2. Now, this saturated fatty acid has 18 carbons. So we're at C18. Then we put a colon and we put a 0. That 0 indicates the number of double bonds that this stearic acid has. We do not count that double bond because that double bond that I have a circle around is a part of my carboxylic acid functional group. That's not a part of the alkyl chain. Next up is oleic acid, which is C18 because it's got 18 carbons, colon 1. Linoleic acid is C18, colon 2. Alpha linolenic acid is C18, colon 3. It's 18 carbons, 3 double bonds. Now, one of the things that's kind of tricky about this that we will get into in just a moment is those double bonds. C18 colon 1, 2, and 3. Well, that notation seems like it's insufficient. 18 colon 1. That doesn't tell us where that double bond is. There are some trends about fatty acids that are worth knowing. First of all, is that your naturally occurring double bonds occur in the cis configuration. Trans fats are something that, heck, in this bag of Doritos, it says trans fats, 0 grams. Trans fats are found in different foods, and for a time in the early 2000s, every fast food company was like, no, we don't have trans fats. That's why your bacon ultimate grease burger from Jack in the Box is healthy. There's no trans fats. Trust us. It's the bacon ultimate grease burger. Would that do anything wrong to you? No. Okay. So trans fats do occur in certain frying conditions and frying in certain fats. Um, and the significance of them is they have to be metabolized in a different way. And so an intake of large numbers of trans fats can lead to a greater likelihood of even greater obesity and other greater risk of what's the term? Uh, Coronary heart disease. Um, so your naturally occurring fatty acids are going to have cis double bonds. The first double bond, here's a good rule and guideline. The first double bond generally is going to occur between carbons number 9 and 10. Now that term between 9 and 10 is worth noting because we see, okay, well, it starts at carbon number 9 and the double bond ends at number 10. Okay, so C18 colon 1 starts at 9. Okay, keep that in mind. Here we got the same sort of thing. Starts at 9, ends at 10. Starts at 12, ends at 13. Now, our polyunsaturated fatty acids, they are not conjugated. So to translate that, what I want you to think about is there's a pattern. I want you to think that your double bonding pattern goes D, S, S, D. So when you have a polyunsaturated fatty acid, like with this 18 colon 2 for linoleic acid, we've got a double bond followed by a single, followed by a single, followed by a double bond, which is my DSSD. In the case of alpha linolenic acid, well, double, single, single, double, single, single, double. So that pattern is most commonly occurring in naturally occurring fatty acids. Now, what I've shown here is the notation for number of carbons, number of double bonds, kind of given a background on where your double bonds typically begin, how they're positioned, but we haven't looked at, well, how do we know for sure where a double bond is? Well, if you've ever heard of an omega fatty acid, specifically like omega-3 fatty acids, think about the Greek alphabet and omega. Is omega the first character in the Greek alphabet, or is it not the first? And if it's not the first, which one is it? Add it to the chat. Last. You're absolutely right. Okay, now that understanding that the omega, or that omega is the last character in the Greek alphabet, is valuable for naming omega fatty acids. And I know that I'm blocking omega fatty acid here. We've got right here a fatty acid that's kind of been flipped on its head. Here's our carboxyl group. What number is associated, or priority is associated with that carboxylic acid there? Add it to the chat. Perfect, it's number 1. Now, what that means is our last carbon, the one on the very opposite end of our molecule, We don't necessarily know what it is, especially when we're looking at a fatty acid like this right here. N. How many CH2s is that? N many. I don't know. Could be any number of them. It could be 7, it could be 12. What we want to do with this is for naming an omega fatty acid is we want to go from here's our carboxylic acid, which gets priority 1. And then we want to go to the methyl group at the opposite end of our molecule. That, we don't really care about the number. We don't care if it's, oh, this is C22:1. What we want to do is we want to count from here to here to here and say, all right, well, how many carbons from our methyl end does our double bond begin? Okay, so this is our methyl end. I'm going to put a star by it. And I'm not redesigning it or renaming it in terms of priority, but just for counting for omega. 1, 2, 3. So that's why this shown here is an omega-3 fatty acid. So if you were to see an omega-6 fatty acid, well, then you do the same thing. 1, 2, 3, 4, 5, 6. And at that 6th carbon from your methyl end, that is where that double bond begins. Now, these are commonly known also as N fatty acids. 16:1, N-3. This N designation tells you where the first double bond begins. Now, when you have something like this right here, okay, let's dissect this. How many carbons does C20:5 have? 20. Perfect. How many double bonds does it have? Perfect. Now, this is where it gets a little bit tricky. Is C20:5 N-3, is that an omega-3 fatty acid? It is. N-3? Yeah, it is. Absolutely. Now, what I want to do is I want to go ahead and draw this molecule out. So, does this mean that only unsaturated? Yep. Yep. 100%. I'm going to go ahead and say, okay, 1, 2, okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. For the sake of the model, I'm going to go ahead and put my double bond oxygen. I'm going to put my H3 for my methyl group. And then what I'm going to do is I'm going to switch colors and I'm going to draw my omega-3 double bond. And then I'm going to fill in the rest of my double bonds. Okay, so carbon 1, 2, 3. Does everyone agree that where I drew this green line, that's where I put my first double bond? Great. So I have 5 double bonds. Well, I've drawn 1. So now I only have 4 left. Awesome. Now, does this explicitly, N-3, does that tell me where my other double bonds are? No, it tells me where my first one is. Do I know where my others are? I do, but I have to remember this. And this is, I always think about this as like gatekeeper information. Like, you can't draw an omega fatty acid unless you know this right here. In polyunsaturated fatty acids, double bonds are not conjugated. So we have a pattern, DSSD. So I've got double, single, single, double. Does everyone agree that is where my second double bond is going to go? Okay, so now I got 3 left. Single, single, double. Now I got 2 left. Single, single, double. I got 1 left. Yep, that's my ad. That's a single, double. There we go. This is an omega-3 fatty acid. This is a 20 carbon long fatty acid. C20 colon 5 and minus 3. Would my fatty acid look different if it was N minus 2? It would. Would actually this really just illustrates like you have to know that your double bonds are not or that they are not conjugated. So you have that DSSD pattern. Double, single, single, double. Double, single, single, double. Single, single, double. Single, single, double. So that's the pattern for an omega fatty acid. Anytime you see N, that's the same as omega. N minus 3, omega minus 3. Now, with that in mind, there are other notations. So the omega scheme or the omega system, that's commonly used in nutrition, and dietitians will use that terminology. Now, chemists, by comparison, well, they have a different numbering scheme, and I want to show that here. Their numbering scheme is known as the delta numbering scheme. And whenever they do that, their numbering starts from, well, which atom has the highest priority? And the one that has the highest priority is the carboxylic acid. So I'm going to jump back and I'm going to show you, okay, well, I'm going to circle this is the omega scheme. So C20 colon 5, omega minus 3. Now, C20 colon 5, delta. And now what I'm going to do is for the delta numbering scheme, I'm going to switch colors. I'm going to count my carbons. 1, 2, 3, 4, 5. This is delta 5. Comma. 6, 7, 8, 9, 10, 11. Is everyone add a Y or yes if you're with me on this before I complete the numbering, and N if you're not. Okay, great. 12, 13, 14, 15, 16, and last but not least is 17. In both cases, we are numbering the double bond where it begins. The difference is, well, where are you starting? Are you starting from the methyl end, or are you starting from the carboxylic acid end? You're starting from the carboxylic acid end, well then, you're using priority rules, as is the case in organic chemistry. If you are starting from the methyl end, well, then your numbers are starting with the opposite direction. Now, given the two, if I have a preference, I guess my preference is the delta scheme, because then it's a numbering scheme that's like, it's a pattern. And you don't have, there's not like any gatekeeper. Here are where the double bonds are. They begin at carbons 5, 8, 11, 14, 17. You don't have to remember DSSD or any pattern of that. Now, with that, when it comes to fatty acids, this is one of the important things about their physical properties. Is saturated fatty acids pack very tightly, and they form rigid, organized aggregates. For example, they form membranes easily. Now, unsaturated fatty acids bend. I gotta close that. So in models A and B here, we have a saturated fatty acid versus an unsaturated fatty acid. Those unsaturated fatty acids, they're straight, and then they have a kink. In which case, here what we've got, well, I always like to think about this in terms of space. If you have two identical spaces, x-axis. We're looking at the width of something. Five saturated fatty acids are going to pack really well together. Whereas if you have a mixture of saturated and unsaturated fatty acids, you're going to need more space to pack five fatty acids. Now, I always think about this in terms of like nutrient density. Like if you're going to eat something that is high in saturated fatty acids, you're going to get a ton of energy from it. You're going to get these fatty acids that have tons of energy. They're great energy resources. But then the question is, are you going to use all that energy? If the answer is no, then it might not be the best idea to use that. If you're like doing the effective, or if you're effectively trying to like, oh, I'm training for an ultra marathon or something like that, well, then you probably do need that energy every single day. Which is why, one thing that I've noticed in my years is, people who are like, oh, I'm super into CrossFit, so I eat 17 egg yolks and three protein shakes before 7 a.m. And I'm like, wow, that's a lot of egg yolks. And they're like, well, have you tried to roll a tire a mile? I'm like, never have. And they're like, think about it. I need that energy. The tire's not going to roll itself. I'm like, touche. You do need that energy and I'm not doing that. So I probably don't need that energy. But look at us. We're both here at the Waffle House having 17 egg yolks. One of us has made a mistake. That one would be this guy right here. On my little camera, it kind of looks like my hand is not actually my hand. Instead, it's just, anyway. Um, so mixtures of saturated and unsaturated fatty acids. Well, unsaturated fatty acids do not pack as tightly. So the space that they occupy is going to be different. Now, this is our last slide for the day because this brings up that packaging. When you have saturated fatty acids, which is what we have at the top of the screen here, 12, 14, 16, 18, 20, 24 carbons. What I want you to notice is the melting point of, let's call it 100 grams of, or the melting point of this N-dodecanoic acid, that has a melting point of 44.2 degrees. If you have a bunch of 24 carbon fatty acids, that has a melting point of 86 degrees Celsius. Why is that? Well, as the number of carbons increases, it takes more heat to heat them because they have more surface area. And these cluster super well together. Meanwhile, if we go down to the bottom here, our unsaturated fatty acids, and more than that, our polyunsaturated fatty acids. Okay, 16 carbons, one double bond. What's your melting point? 1 to 0.5 degrees Celsius. So if we compare that, this 9-hexadecanoic acid to palmitic acid, what's the difference between those? One double bond. That singular double bond drops the melting point of hexadecanoic acid 62 degrees roughly. Now, if we go on from there and we say, all right, well, our next one is oleic acid. That's 18 carbons, one double bond. Compare that to N-octadecanoic acid or stearic acid. Stearic acid versus oleic acid. Stearic acid has a melting point of 69.6 degrees Celsius. Oleic acid is 13 degrees Celsius. So what do we see there? Well, our number of carbons increased. The number of double bonds stayed the same between here and here. The presence of a single double bond still drives the melting point way down. Now, if we take a look at oleic, linoleic, and alpha-linolenic acid, one of the questions that I like to think about with respect to these, and I think that it's worthwhile for kind of your exam and stuff, is this a solid or a liquid at room temperature? Oleic, linoleic, and alpha-linolenic acid. If room temperature is 23 degrees Celsius, all three of these are liquids at room temperature. Compare them to their saturated counterpart, stearic acid, 69.6 degrees. That is a solid at room temperature. Then, if you get all the way to the bottom, arachidonic acid, that's got 20 carbons. It's 4 double bonds, has a melting point of negative 49.5 degrees Celsius. That is a liquid at room temperature. The only place that that's not going to be a liquid is if you go into a research lab and you find a minus 70 degrees or minus 80-degree freezer and you put arachidonic acid in there, it will then freeze and it will then become a solid. But in a standard freezer, in a refrigerator, that is a liquid because the presence of all these double bonds, despite those number of carbons. So your kind of takeaway from this is that as the number of carbons increases, your melting temperature increases. As the number of double bonds increases from 1 double bond to 2 to 3 to 4, what happens to your melting temperature? Your melting temperature goes way down. Now, that is basically what's in blue here is your important takeaway here. I don't want you to be like, oh, but what about solubility at 30 degrees Celsius? I'm fine with that not being a major part of your daily life, because they're typically not going to be very soluble in room temperature. And then, yeah. Oh, and this slide, this just goes on to kind of detail and compare the delta and the omega numbering scheme. On Friday, we'll pick up at slide number 8. So I'm going to skip over 7. I'll touch on it for a little bit, but then we're going to go on to slide number 8, where we talk about triacylglycerols and triglycerides. Those two terms, triacylglycerol and triglycerides, those are interchangeable terms, though. But I'm going to go ahead and stop my share. I'm going to say thank you guys for coming to class. I hope that you have a wonderful Wednesday. I hope you have a wonderful Thursday. We will not meet for class tomorrow. If there's something that you want to meet with me about tomorrow, then I think I can probably accommodate that. Just send me an email and I'll try to set up a time. But you have nothing due tomorrow. And I'm still working on a practice exam. And I'm trying to simultaneously work on a practice final so that I'm not like, hey guys, guess what? Your final's on Friday, but it's Thursday. I got your practice final done. That doesn't really help very much. And I'm happy that I recorded myself doing that ridiculous smile. I'm going to stop my recording right now.